Teardown Tuesday, where we explore all things electronics, really. We take apart cool products, we do some reverse engineering, we find out how they work, and most importantly, lately, we design cool open source projects for all of you guys. Now, if you've been following along with our series so far, you know we're doing a Strymon MIDI-fication project where we reverse engineered a Strymon Deco, part of the Strymon Smallbox series. And we're creating a replacement control board for it that allows for full MIDI integration. You get USB-C, maybe some other extra little goodies that aren't going to be found on the new sort of reissues. And it's a really important project, I think, because there's going to be so many pedals out there that might sit dusty in a drawer, or even worse, end up in landfill. And we're going to bring those up to snuff with, industry standard MIDI and beyond. So if you've been following along, we've been doing some PCB layout. We've been getting a hardware PCB. Of course, it's a hardware PCB, but we've been getting, a rough placement worked out so that we know everything's going to fit. We're looking at our controls, how it's all going to work. We've got this little daughter board here for the USB-C. The 3.5 millimeter MIDI in and MIDI out. So something really nice. You get separate MIDI in, MIDI out, no special cables that you'll need to buy. And we're probably going to look at making a nice little faceplate to cover up that large USB-C hole there, because we want to make sure that anyone can install this themselves. We'll provide a drilling template, and all you need to do is just have a hand drill and some basic drill bits in good working order. So without further ado, let's get back into it. Now, in preparation for today's stream, I've gone and made a couple of, just added a couple of parts that we're going to need. So if we hide this control board here, you can see I've got this footprint that doesn't yet have a 3D model, and that's because it is an FPC connector, and it's actually, there's basically every part you get from every line from every manufacturer is slightly different, so it's quite hard to find exact 3D models for all of them sometimes. So this is our daughter board, and I've just gone ahead and added some of the components that we'll need for our USB-C connector, as well as our MIDI input and output circuitry. And then this is an 8-pin FPC header here. I don't know if we can see those pins. Yeah, you can see 1, 2, 3, 4, 5, 6, 7, 8 pins. It's a 0.5 millimeter pitch header. Now, bringing our control board up. Hello to everyone who's tuning in. Let me bring the chat up in case someone says hi. So hello. If you're new to the stream, then feel free to leave a comment, say hi. If you're working on a project, something cool, then let us know about it. We'd love to shout you out on the stream, and just let us know what you guys are up to. And this is meant to be really interactive and community driven. So if you have an idea or a suggestion, if you have something you'd like to contribute as part of the design process, drop it in the chat, and we'll take a look at it for sure. So as you can see, I had to go ahead and create an extra little cutout in our main board here for this optocoupler. It's quite a large component if we go down to the bottom. If you're not aware, by the way, we're using Fusion 360 for both our 3D and electronics CAD design process here, because it has a free hobbyist license. It has had some more limitations in past months, been a little bit controversial, but it's still got an excellent hobbyist free license. You get very, very competent industry capable 3D modeling, as well as electronic schematic PCB capture capabilities. They have an educational license, which gives you access to the full version if you're a student. They also have a startup license, which gives you, I believe, 3 years. I think it's 3 years of free access to pretty much the full version of the program. I think you get the extensions as well, plus unlimited cloud credits for rendering. It's not sponsored by Autodesk, by the way. Reach out if you're from Autodesk. Would love you to sponsor us, but not sponsored. It's just I think they do have some really solid deals. The startup license, as long as you're doing under 100K in revenue, something like that. Yeah, I think you get for free. So anyway, you can see we've got this board, and what I've tried to do is give it a little bit of tolerance, because this is going to be hand drilled, not precision CNC. It's important that there's some tolerance. So I've made sure this board has a lot of, a reasonable amount of room from that edge, and probably need to bring that in a little bit to give it some more room away from that edge of the pot. I don't see that being an issue. That'd probably be quite useful. There's not too much we do. I can probably bring that edge of the PCB in just a little bit. We might be pushing the tolerances there, but alas, and you can see in the enclosure, this is the current state of affairs. So welcome, if you're tuning in, let's dig into it. Now, what I want to do first of all, let's just hide that sidebar so we've got a bit more room to work with here, is we're going to add, we've got another FPC, so a ribbon style connector. What is really annoying, if you somehow are watching this and you're from Autodesk, dock left, dock right, it seems like every time you resize your window or anything like that, it resets these preferences and it drives me insane. It should just default to whatever you had it. So when I click dock left, I want it to stay dock left whenever I open the program unless I explicitly tell it to. Thank you. Don't spend too much time ranting about the things I don't like, so I just gave it a big plug. But you know, no software is perfect, and this isn't a shill piece by any means. So what we need to add is the 1mm 16-pin connector. I'm just checking the comments because comments via Facebook don't show up with the names by default. Cool. All right. So we need our 1mm FPC/FFC connector. So here, what I did is I've just kind of created a dummy template for what the signals from the actual control board are, and it was quite interesting. I shot from the hip a little in a previous stream and said that this whole control board operates at 5 volts. And that's not quite true, I discovered. I was sort of, I wasn't up to really getting the pin out of that connector yet. I just measured the pot values, assuming that they would be at whatever the operating voltage of the I/O of the main processor on board. I was wrong, quite wrong. This main board, let me take the ribbon cable out. This main board, we did a sort of a teardown, a reverse engineer, and I can't remember exactly the outcome, but I'm willing to bet this has a dedicated DAC because this DSP probably won't have, I could be wrong about this, but probably won't have onboard DACs, ADCs to convert our pot voltages into digital signals. So I would assume that there's an ADC on there running at 5 volts and then has, like a 3.3 volt logic interface, because the switches and the LEDs all operate at 3.3 volts. Well, the LEDs obviously don't strictly operate, they're a current driven device, but the switches have a pull-up resistor to 3.3 volts, and this toggle switch also operates between 3.3 volts and ground. So I've created a bit of a pinout here, and it might be a little confusing, but it's basically a left. If you rotate all of this, let me see how well this is going to line up with the camera. Right, if we rotate all of this 90 degrees that way, hopefully you can still read that. And I hope this isn't mirrored, but this side, let's see if I can do this without getting too much glare of the camera. So that side of the connector, cool. So that left side is that pin there. All right, we've got these alternating rows. The only thing I couldn't puzzle out is you see these toggle question mark nets here. And that's, I'm a little unsure. They don't seem to connect to anything. So this toggle switch, if you look closely, actually has 5 pins on it, sort of solder headers. Connecting the toggle switch, and it's a 3-way toggle switch. They have on, off, on, which only needs 3 pins to operate. And I thought, well, they've added some extra pins for stability to the main PCB, all well and good, except those pins actually connect to the header. I'd love to be proven wrong. I've, using a light box, I've traced out the boards. I can't see any traces running anywhere useful to those pins, but they definitely do run from that soldered header to this FPC connector here, and they don't connect to anything as far as I can tell. So a little unsure. I think maybe they were allowing for a different switch in a design revision, perhaps they had a couple of different types of switches, or early in the prototyping, not sure. But this is an interesting case, the Deco, probably not the best one we could have started with, because the idea is to create a fairly general purpose control board that we can then, with some very slightly tweaked firmware, use for all the Strymon small box devices. But the Deco has a slightly different layout. You'll notice pretty much every other one, it doesn't have this middle switch here. That potentiometer goes down, and then you've got two toggle switches here. So what I suspect is that, in fact, now I'm verbalizing, and I'm only just realizing this makes a lot of sense, that they're using the same FPC header, and those other two toggles are for sort of toggle switch A and toggle switch B. It makes sense to reuse as much of the topology as possible, and then you're just adding another switch and changing the layout. Only just realizing that. Thank you for being a good soundboard. That's I guarantee that's what they've done. Almost guaranteed it. So anyway, I've gone ahead and created our header here. Obviously, I haven't pushed that to the, maybe I have pushed it to the 3D PCB, but it's so far off board. But it is going to sit round about there. Now, what I should do is go ahead and measure the distance of the header to, I guess, the edge of the LED, and that is 4.85 millimeters. All right, 4.85 millimeters. Now I'm going to measure the full width of the connector that's on board here. That's going to give us, what's that, 23 millimeters. Okay, so halving that, we get 11.5 millimeters sort of from the center, plus 4.85. Let's bring up the calculator here so I don't forget. So what did I say? 11.5 plus 4.85. So we get 16.35. Keep that on a calculator so I don't forget it. Now we're going to take, measure the diameter of the LED standoff again, and it's 6.5 millimeters. Okay, so half that again is going to be 3.25. Now we can assume with some degree of certainty, therefore, that the center of our connector to the center of this LED placement here, so the LED is there, highlighted, and our connector is there, they need to be, what did I say, 19.6 millimeters apart. I'm going to fudge it and call it 19.5 millimeters apart, so it's just nicer on a 0.5 millimeter grid. And the reason is you don't want, 0.1 millimeter is fine, but you want to have as little, I guess, strain. Let me see if I can hold this straight. Strain on this flex cable. You don't want to be bending that way. It only is designed to fold over this way, as much as you can help it. But as I said, 0.1 millimeters, that's well, within the tolerance of all the rest of the things, the stuff. All right, so 31.5. What did I say? 19.5. Okay, so we want this to be 12 millimeters. There. Okay. Sorry, actually, forgive me. I've got the mega itchy nose today. All right. Cool. Well, I like that. On this, you can see it's sitting quite close to the edge of the board, so I don't know in our 3D model how close it's running to that foot switch. I guess let's push it and have a look. So if you tune into last stream, good habit. I think this latest version of Fusion just seems to have some instabilities, or maybe it's something in this design. But updating multiple 3D models from various sources into the same, into the one model, so our kind of master project file here, was causing some stability issues. So we'll see how we go. But I just want to make sure that it's fairly clear. Yeah, so it can go a lot closer to the edge. You can see, again, I haven't got an actual 3D model here, but I can use this silk screen outline as a pretty good, I've actually measured that off the data sheet, pretty good indicator of where it needs to be. So it needs to go that way a bit more, but let's just save that. I want to make sure it's clearing that foot switch okay. It obviously should, because it's already a pretty similar size connector there. Yeah, beautiful. So that's going to go down there. Lovely. Now we need to add a matching need to add a matching. So we've got this connector here. So let me get rid of the enclosure. And where's our control board? There. We've got this 0.5mm connector, and this is going to connect our daughter connector board to our main board. And the way I'm going to do it, I think, let me get rid of those foot switches. They're a little in the way. Is part of the issue is if I put it just like there to there, kind of going straight, then I would have to have a ribbon cable that had the contacts on different sides. You can see on this one and most ones, the contacts are on the same side of the connector, but that wouldn't work if I wanted to use this same connector that has bottom contact mounts, or I'd have to get a special one with two, like top and bottom. They're more expensive and a bit bulkier. So what I'm going to do instead is run it from here and then loop around. Let me go to a side-on angle. We'll go from here and then loop around and down. Gives us two advantages. One, we can use a more common type of FPC cable on the same connector here, but also it's going to give it some room to move in that as we assemble it, which is going to be important because this board's going to go in first. So having it loop back around there is actually going to be to our advantage, certainly. So that's looking pretty good. Now, what I do want to have a look at is on our TRS board, I'm going to call it our connected daughter board, where that is. So it is 9.5mm, and that is minus ½ millimeter. Okay, so it's 10mm. Which no, not quite in line with the USB connector. It's 10mm from that standoff there. Okay, so I can use some. I don't know if they're going to line up with the enclosure perfectly, but we can get pretty close. In fact, how big is that edge there? 8.9mm. What we might just do is sort of. No, I don't want to do that. Okay, 10mm from that standoff there. Now, in our enclosure, let's look at the dimensions. I'm just trying to work out the position. All right, so, and it is the one closest to our USB-C connector. It's 10mm from that hole. Let's measure. That hole from the center of our enclosure is 19mm. Okay, which means it needs to be 9mm from the center line. I'm assuming that that center line matches that center line. If not, we'll quickly find out. Okay, let's close that. Now, where's our control board? So what did I say? 9mm. I think I need to go and add that connector still though from the board. Connector 8. Oh, I need to update that, do I? I mean, I need to update that. Well, the library should be there. Are you kidding me? Hang on a second. Let me spare that side screen for a minute, because I'm going to have to... This is... Okay, I know I go on about it every week, and I don't want to beat a dead horse here. But Fusion really needs to get their act together with regards to library management. It's a lot of garbage and nonsense, in my opinion. So if we go, hang on, let me go back to the main screen. All right, let's open our library manager here. Fusion team, I should see our connectors. Yeah, so it's being used. Why don't you like this? I'm just going to delete that connector there because it's not liking that. And where is that at? 12mm. All right, we're just going to. This is such a clunky way of doing things, but let's add that back in. we've got sort of this two-part schematic symbol. I'm going to add our 8mm connector there. All right, all good. I think just the library hadn't updated or whatever garbage nonsense was going on. Where are our connectors? They're all the way down here and here. All right, so this guy needs to be 12mm from the center. Make it nice and close there. This guy is going to be looping back around, so it's facing that way. I'm going to say 9. Ooh, well, we can't go there, so it's going to have to be a here kind of thing. Let me just sanity check and see if kind of lining up with those pot pins makes sense visually, which no, it doesn't. It's a lot lower than that. What's oh, that's not the. I haven't lined that up with the center of the enclosure. Of course, I've lined that up with the center of the board. Normally, I do try and make the center of the board the center of the enclosure, but in this case, I have not, just to simplify some of the mechanical drawings, because we had to back calculate the dimensions from the enclosure. So what we might do is get the distance from there. So 7.9 millimeters. Okay. Center there, it's 6.25 from there to the center. Okay, so 6.25 from the center of that pot to the edge of that pot, and then from the edge of that pot, actually, hang on, I can just use that directly and go to the control board for a second. Can I go like that? Okay, lovely. So 14.14 to that edge, and then from the center. So remember that 14.14, and it's 8.9. So, oh, we don't want to full screen that calculator. I say 14.4 gives us 18.59. I am going to abbreviate that to 18.5 because that's how we're going to do things. Okay. 18 point. Oh, really? Seems a little excessive. Yeah, it's going to be pretty tight against there. Okay, well, we might have to kind of snuggle it down here, I think. 18.5, all right. Well, that capacitor is going to have to move down there, say. Oh, 18.5. Okay, well, is what it is, I suppose. All right, let's push that, and now things should be mechanically falling into place, and we can put our electronic components, our microcontroller and supporting bits and pieces all around it. Should be nice. Okay. Cool. Save. All right, now let's bring that in. Sort of around there. And that should line up. Oh, look at that. That is satisfying. Or is it? I think Fusion's done the old freeze when updating the main model trick again. Please don't do this on me. Experienced this enough to know that just shutting it down is the quickest way to sort this out. The old force quicks doesn't resolve itself. Yeah, it's something to do with the internet connections. So I go to like force quit it or end task, and it pops up saying it's some sort of like internet connection error. And so I'm all for, you know, internet connected applications, sure, except can you at least not make them crash when something like this happens? It's so frustrating. So frustrating. Okay. I don't really need to open recovery for any of those, because all we were doing is updating our main reference model. Give me a second, make sure I don't reveal any upcoming gizmos that aren't ready to be sort of, I mean, I don't really have any in design, but where's page just to double check. Okay. No, don't care about that recovery file. It's going to update you now because everything else is saved, so we didn't really lose any work because we've already been stung by this. Now, if we go down here, you can see those connectors should line up pretty much perfectly. You know, not 100%, but probably as close to it. You can see how far off they are. Yeah, less than 0.1 of a millimeter. I'm okay with that. I'm okay with that. No, we don't want a recovery file either. Okay. All right, so that's looking good. Like I said, I do want to just give that a little bit more, give that connector a little bit more tolerance because it's, it's going to measure the angle as it will go from the edge. 1 millimeter. That's could be better. I'd like to have a bit more tolerance on that, if possible. So anyway, we can start laying out the rest of our board now. I'm just going to see if I can push that. No, there's no room to push that back. Maybe 1/4 of a millimeter, but it's not really making much difference at that point. Oh yeah, let's just run a DRC and double check that that isn't going to violate it. Yeah, it is going to violate it. So maybe we just move, going back to our project, maybe we can move everything this way. But then we run into issues with the foot switches. Although, where's the deco enclosure? Yeah, so part of the issue is the foot switches, or the enclosure is keyed so that the switches can't just go in any orientation, which means they will be in that orientation, so we can't, you know, rotate them sideways or anything to give ourselves a bit of extra wiggle room, unfortunately. But I think that's probably going to have to do, if I'm being honest there. So a little bit tight, but what can you do? Nice if we had some shallower ones and we could just, that's what it is. Anyway, sorry, my hay fever is just going wild this morning. Let's start laying out our components and looking where everything's going to go. So generally speaking, I like to work on a metric grid when I'm laying out components because I just, force of habit, I guess, and, you know, the way that components are sized, I like to work on a grid using for component placement, generally 25 mil So that's mil thousandths of an inch, not millimeters. I mean, I know that we want to keep that, we don't want any tall components going near where our flex cable's going to be, but this connection here also has our, is going to carry our USB signals, and we don't want to have our microcontroller all the way on the other side of the board from a USB signal. So it's going to be about here. It's going to be somewhere about here. I'm going to make it a bit closer this way so that if we do, put a pot in there for a different form factor board, we've got a little bit of room around there. But I'm going to look at our decoupling capacitors. So if I go back to our electronic design here, we've got these decoupling capacitors here, which all need to be as close as possible. So C19, 18, 19, 20, 20, then 21, 2, 3, 4. So 18 to 27 all need to go here. Now, a trick I like to use is I actually like to use the command line for things like this, because you can just type move C18 and it'll just snap to your cursor. You don't have to go hunting for it. Move C19. 20, C21, and you can backslash to go to the command line. It's good when there's a specific number of capacitors that you need to bring up to a point. They might not all be clustered around the same spot, and rather than having to go hunting for them or click and drag them, you can just really quickly bring them up here. Okay, so tissue. We've got pins 44, so C24 needs to be connected to pin 44. That's part of the internal core voltage regulation. So C24, where's pin 44? On the other side of the package, isn't it? Okay, so there. It's going to need to go, I'm just loosely placing these. Okay, so I can work out where stuff needs to go. Ideally, using 0402 components would be better for these decoupling capacitors. Certainly the 100 nanofarad ones, but look, we use 0603 for pretty much everything else. That you're not going to get a noticeable performance difference, really. I know some people say, well, the smaller the package, the smaller the inductance, and you can get an extra 0.5 millimeter maybe to the chip, but it doesn't, unless you're dealing with high-end FPGAs and DSP chips, that kind of performance difference, if you're putting them on the same top layer, is not actually, it's just really not required apart from really high performance stuff. And if you're doing that, then you already know this. So we've got 6 pins, 1, 2, 3, 4, 5, 6. These pins here. Let me just double check. I'm going to look at the design for hardware sections, because I think they missed a couple due to size. They sort of fudged it a little bit, because I'm looking, we're 2 caps short in terms of how many pins we have and how many decoupling capacitors here. There's a trade-off here. Pins 48 and 49 share a single capacitor, so that's interesting. So let's go back to the main screen. Pin 48 here is the USB power. 48, 49. Oh, that's probably here in the IO VDD, because they're next to each other. Okay. All the trade-offs. 43. I'm just trying to. Oh, okay. Anyway, that looks all right. So 48 and 49 are going to share a C9, which it's C9 for them, which is one of the 100 nanofarad capacitors. So we're going to put one of ours on 4849. We're just following their recommendations because there's no need to do the the engineering math twice, and a lot of this is just rules of thumb anyway. So if you have an example and recommendations to go off, you're mad not to take advantage of that. So they're going to be sort of, I'm going to turn off ignore violators so I can put these just really close together and then work out the exact spacing later. Surely overlap a bit. I'm going to switch to a 12.5 thou grid here. It's going to be 44. Cool, and then 48, 49. That actually needs to go a bit closer. Really great. Pin 43. What's that? That is okay. So it's going to have another decoupling capacitor next to it, I guess. Although, fortunately, I've got the same layout here, so I can kind of cheat a bit and just look at their, where they're routing things here as well. And it's interesting because that pin 43, that should be that one there. And that doesn't look like it's connected to a decoupling capacitor, which I find really interesting. So see, let's get 43 there, and that's that pin on the edge there. Do they say anything about pin 43? Nothing. So this is really important. Basically, getting the decoupling for your your high-speed digital components like a microcontroller is more or less the most vital part of digital design like this. So it's just interesting that because it looks like it's connecting to ground there, which is really strange. All right, so we can see here that pins, what's that? That's 48, 49. Then 50. Oh, they're resistors there. So that's probably for, is that 1, 2, 3, 4, 5? So 1, 2, 3. Yep. So that's going to be our USB lines, I'll bet. So we're probably going to need to rotate this 90 degrees anti-clockwise so that those USB lines line up, I'll bet. What pins are they? 46 and 47. Where are, yeah, okay. So R13 and R15, they're our terminating resistors there. So wait, so they were 13 and 15. Okay. Hang on. Move R13 there and move R15 to there. Let's flip those. So yeah, I think we're going to have to move our whole design, rotate our whole design that way, so that because those terminating resistors there are to help prevent reflections along the line and ensure that we have the right characteristic impedance. So we want to make sure they are as close to this microcontroller as possible, but we also need to squeeze our decoupling caps in here, which is where 0402 components would make this job a lot easier. So decoupling caps are going to have to, it's a bit of a trade-off here. But honestly, they're not far enough away to really cause any significant issues. What I am just curious about is that in this, whatever this plane is, oh, unless this is a 3.3 volt. Yeah, because they're going to vias. Okay, so I realize the confusion. So in this is actually a power plane, not a ground plane, connecting to 3.3 volts. So, okay, gotcha, which is why that's 3.3 volts. That looks like it's connecting to that ground plane there. And then you have 45, which goes to C8 in their schematic, which is this 1 microfarad here. So, okay, well, what we'll do is that, which is that one there. So that's going to kind of go up there. Then we've got 43. We've got some decoupling caps there. 43 and 42 are also more power pins, I believe. They are, and 42 will be in there. Okay, so put some of our capacitors. Let's keep track of the numbers. So, 21, 22, it doesn't really matter which ones we're using here. To go there. Oh, let's try there. There. It's probably as close as we're going to get realistically, I think. It's going to run there and there. Okay. All right, now C18. These 1 microfarads are a little sort of more, not special, but okay, so those 3 are going to 45. I missed a trick here. 45. 45 is meant to be C18, not C24. Okay. Yeah. C18 is going there. Yep. Gotcha. Okay. Cool. Then 19 and 20 going to go to these ones. So what's that? 23 and 50 by the looks of it. That's our digital kind of stabilizing core voltage there. Although that's connecting to 1.1 volts there. Sweet. So 19, 20 going to 23 and 50. Hang on, what capacitors are they again? 19 and 20. Okay. So 19's here. Where's pin 50? There. Shame we can't get that any closer, isn't it? And we're going to have to dodge the quad spy nets. So that's decoupling to pin 49. Might have to try and squish these all up a little bit, I think. So if we switch to a 6.25 hour grid, then we can probably bring this up closer, and then can bump all of these up a little bit. Just get them nice and tucked in. It's a little better. It's going to make things a bit easier. Still like kind of further away than I'd like and a less direct route, but I'm not sure there's too much we can do about it. That said, you know what we might do is move our USB resistors out a little bit, because it's USB 1.1, so it's running at 12 megabits a second. The speed's not that high, and that little bit of extra distance between our pins. I'd put it this way: I'd rather have really good decoupling for the microcontroller, so that when it's trying to slurp up that current for its clock edges, I'd rather it have access to really good clean power via that decoupling and just because that realistically it's not going to introduce that much of an issue, reflection error with that bit of extra distance, but that shorter decoupling is going to make a significant amount of difference. That's for sure. Okay, I'm liking that. Probably bunch that in a bit and bring our USB traces sort of through it there. All right, that's better. That's better. What else do we have left here? We've got C20. Nah, just all these network here. So what have we decoupled here? Oh, I wasn't even on the main window. Sorry about that. We were just I just moved our USB resistors here and away to there. Can you see my cursor's not? Ah, there we go. Yeah, let's go click on the window. So yeah, move those just a bit out so that we can get our decoupling capacitors more direct there. So, all right, a side window. We've got 42, so 33, 22, and 10, and 1. All right, so jump back here. One of these at 1. Out there. And because we've got this ground pad in the middle, we don't have to worry about, we just want to have that 3.3 volts as close to that power pin as possible. Whereas on, for example, QFP packages, whereas this is a QFN where you don't have a center pad, you have actual leads coming out, you would have pairs of power pins. So that would be 3.3 volts and ground next to each other, and you'd want to have it more like that so you can run the traces directly there, usually with VIA in between. But that's not the case, and we get a bit more layout flexibility along with the extra pins because we've already got that big ground pad. So what do we say? 1, then pin 10 needs some decoupling. So we'll probably put him there. We are going to have to move up a bit, I think. I'm definitely going to have to move up a bit, but I've got some more room here, so I can probably get away with that and moving those in a bit. It's going to make our escaping these pins a little bit more challenging, but not by a big deal. It's still going to be pretty doable. So just want to get a bit of breathing room around that connector there to escape some traces. Get these ones right up close. I'm going to try and bring them all in as much as I can when I've got them roughly in the right places. Then we need 100 nano on 22, which is there. Beautiful. Wait, no, is that? It's our ground pin. Where's 22? It's there. And then 33 is there. And I've got this spare 1 microfarad C10, make sure it's close to pin 44. If you look here in the hardware design references, make sure C10, which is this 1 microfarad we were referencing before, it's close to pin 44, which is the VREG pin. All right, well, we can do that. Pin 44. All right, that's what we will do. Put it up there somewhere. So we're going to have that running there. That running there. Okay. I'm just wondering if I can bring in a little bit further. That might be pushing it. Nah, I think that's going to be good. And now they're getting nice and close to those power pins. I'm going to squish them in a bit more by switching to a smaller grid. It's packed in nice and tight here. Lovely. Give it a bit more room because it's in line with that one. That's actually bring that down a bit there. It's going to there. Great. Okay. Okay. Well, that's looking pretty good to me in terms of our decoupling. The only thing I'm thinking of is just moving it this way a touch. Because wary of whether if there's a pot there. Although in the rest of the templates, the pot's actually up a bit higher, so we're going to have a bit more room than I thought. So yeah, I think we'll just select all of this, move it, get a bit of clearance away from that pot and the connector. Oh, did not want to rotate that. Let's try again. Yeah, that's better. That's going to be better. It's a little bit further, you know, USB lines are a bit further away from this connector. But like I said, the having perfectly matched like differential pair impedance is not super critical. Honestly, for USB 2, USB 1.1, you can kind of lay your board out however you like. Within reason, it's not overly critical. If you're doing, you know, USB 2.0 high speed, which is 480 megabits, yeah, it starts becoming really critical. That's half a gigahertz. That's getting pretty quick. And your edge frequencies, which is the most important thing, are going to be pretty fast. So they need to be, because the higher your actual, you know, bit rate, or the, you know, your kind of transfer frequency, which is the 480 megabits, then the higher your edges have to be, because it's not actually how, you know, many bits you send per second, it's how quickly that rising edge happens. Because think about it, when you're transmitting a bit, your signal is either high or it's low, and when it's in the high or the low state, it's DC for all intents and purposes. It's not changing. So the more DC you have in there, who cares? It's actually to do with how quickly that edge rises, the slew rate. Because if you're transferring it faster, you obviously have less margin for error in terms of how quickly it can shoot from, you know, between your negative and positive rails. To make that speed, your eye diagram becomes much more precise. And so if you're, you know, if you have a slow speed, you can have slower edges, and it's the edges that contain that frequency, and in particular your high frequency noise. And the faster that edge is, the more high frequency, you know, kind of aggressive content that you're going to have to try and manage. So for this slower speed, not a problem. Great, so it's kind of going to sit somewhere there. We can probably bring this all in a bit if we wanted to. Do we want to? I do want to leave some room for adding signals out. I mean, it seems like most of this edge here, fortunately, is just decoupling USB and quad SPI. So we're not actually squishing ourselves up too much. But all right, we'll leave it there for now. I'm just going to loosely start placing some components. So we've got our quad SPI package. Now we'd be mad really to put it anywhere other than kind of here, because we've got all these pins running from there. So realistically, doing something like that's probably going to be our best option, because I mean, just, although then we've got this overlap. It's not that pretty. Yeah, doing something like that, so we can just run those pins down. They're going to come out. We'll have a little bit of crossover, but it's not the end of the world. Probably something like that. There's no pin 1 marking on this component package. It's interesting. I'll have to rectify that, because pin 1 we should have a little dot there. Make sure I fix that up for next week. Definitely not best practice there. And I believe we had a... where are we? What I might do for next week too is try and split the view so you can see the schematic and the PCB at the same time. We've got C28, R11, R12, and switch 2, which all need to be fairly close to our quad SPI. So where are we? Move C28. Here we go. It's the decoupling there. All right, what I am going to do is just move this connector as far to the edge as possible. Just get it out of the way, because this is really starting to become a little squishy. So that was a little bit breather. And this isn't necessarily the final spots that they're all going to sit. I just want to try and get things roughly where they're going to be. Move R11, R12. What did we say? Move S2. So this little foot switch here. And this is a boot select switch. Okay, so It's not critical. We can probably move this decoupling cap there. Maybe how much room do we have on that PCB? Not much. Okay, so there's no wiggle room on the edge of that PCB. We put it there somewhere and put our boot select switch because it needs to be accessible. Put it down there. Oh. Far enough away from everything. That's not going to cause any real headaches. Slot these resistors in here. It's a bit cramped, but it'll do. Yeah. Why not? More than a bit cramped, but not the end of the world. It's probably going to squash in there, I'd say. Be nice if we just had a little bit more room to tuck that capacitor out of the way. Just to be wary of it being, too close to the edge like that. Realistically, it's probably not too close to that LED for pick and place tolerance. Yeah. Okay. It's no closer than that switch, that's for sure. And the LED is tiny. So we could probably just shift that around there because those ground pins we don't really need to access that much. Go there on the edge of our board. Yeah. We can just give ourselves a little bit more breathing room there. Make them nice and aligned with the center of that component. All right, that's better. Cool. Now, part of the issue is though we've got this ribbon cable coming out here, and I mean that's not an overly tall component. Might just save this and go to the 3D view so I can see where that is. Welcome if you've just joined, by the way. We're starting the component layout and some of the kind of PCB placement and routing, which is if you've heard of measure twice, cut once, you can think of it as place twice, route once. And why that is, let me explain. If you do a really good job of your placement, your component placement, your layout's going to be fairly easy, or much easier than it would be if you didn't spend that time, because they're really well considered. And if you're thinking about how you're going to route it as you're placing, you're going to make your life a lot easier. Your PCB is going to be better designed. You're going to have better performance out of it. Whether you need it, if you're designing a tube screamer clone or whatever, the frequencies are so low, like it's audio, it doesn't matter. You can pretty much put stuff anywhere and connect it up however you want, and it's going to be just the same, really. Obviously there's a couple of good rules of thumb, but it's not a big deal. But if you just take the time, one, it's going to give you a better board, but two, it's actually going to save you time in the routing because things are going to be more logical to connect up and have more room and things like that. If you're wondering why that model looks so ugly there with the pins, it's because they're sort of sprung. They're designed to kind of clip in a little bit more. Oh, got a pitch invader. Hey, buddy, Daddy's streaming. I'll come and say hi in a little bit. Can you close the door, please? You can't come in there. Thank you. Little pitch invader. All right. Yeah, it's actually a bit tall. I thought it's starting to get a bit dicey in terms of the FPC cable there. That's really not great, is it? Tell you what I might do, what I didn't even consider, is we just rotate that toggle switch and give ourselves more room that way. I don't know why I didn't think about doing that before, to be honest with you. But let's close the door, buddy. Let's unlock that. Yes, mate. Hey, I said you can't come in here, mate. Can you close the door, please? Hugo. 1 minute, folks. Hugo, no. what are you doing? Do you want to come and see what Daddy's doing? All right, come here.
That's working. That's a lie.
Daddy's working. That's right. Just say hello. Just say hi. Look, here you go. Can you see yourself in the camera? Look there. Whoa. All right, now you can sit on Daddy's lap as long as you don't press anything. We're going to save this just in case, to be safe. All right. So yeah, I think we might need to move all of this way a bit. There really isn't enough room to clear that cable assembly. Yeah, I mean we can probably move this in this way a bit. Definitely not ideal, but he's in here with me. Okay. All right, what do you think? Is this a good PCB layout or a bad PCB layout? Hey? Yeah, it's good. All right, thanks, mate. We're designing this. Look, designing something to fit into this. Okay, that's a little better. I think that will have gained us enough room for that cable to be inserted in and then go up, and yeah, I think that's going to be fine. So now that's a lot closer to there. We'll probably do not touch. No touchy. All right. We just entered challenge mode here, folks.
F.
There is the letter F. Good boy. Been learning all about the letter F, haven't we? Now, what else do we need to place? What's kind of the next most critical thing? We're working in terms of critical placement. And I should have placed this crystal along with the decoupling caps before anything else, because it's going to be the next most critical aspect here. While I'm here, I'm going to group the reset circuitry here. So C29, R14, and switch 3. All right, so move C29, R14, and I'm going to say S3. S. You love the letter F, don't you, buddy? What word were we learning last night? From Donaldson's Dairy. That's right. Now, our crystal here is probably the most sensitive thing on here to get right. So R16, C30, C31, and then our only crystal. So, all right. Move R16, which is our 1K dampening resistor. Move C30. Move C31. Here, move Y1, which is that crystal. Fortunately, it's over on the other side here. So actually, it's a pretty good... That's right, mate. It's a pretty good chip layout. Some chips you get have awful layouts in the sense that it feels like the chip designer didn't really understand how a typical PCB was going to be laid out with it. But, got to hand it to the Pi Foundation. This is a very well-designed chip in that you've got. You can kind of fill up that side of the chip, and then there's not a bunch of, I/O here that you're going to want to escape, really, unless you're not using the quad SPI. So that's quite nice. All right, gonna have to make some compromises here. I think we're going to bump that out of the way so we can run that dampening resistor for our crystal. Actually, I'm a little in two minds here. I wonder if they give a recommended layout. Let's go back to this side screen. Crystal oscillator. They don't give anything about the PCB. I mean, this isn't specific to the Pi. It's just this is general PCB layout rather than anything in particular. Yeah, bud. All right. I think you need to run out to Mummy, okay? Mummy! Can you open the door and go out to Mummy, please?
No.
Hugo, hey, Daddy's working. You're not supposed to be in here, mate. 1 second, folks.
Come on, buddy. How do I?
Just
Almost put in my hat.
all right. Let's get back to it. Alrighty. Check if there's any comments I've missed here. Lovely. Hum. All right. Yeah, so let's ignore that. Let's go back to our main screen. Now, I'm just trying to work out the best way to place this oscillator here. It's almost certainly going to be like that. You know, we probably can get away with that. I just want to keep, generally speaking, you want to keep the, any kind of crystal traces. We're going to have a ground cutter. We don't want any, you know, sensitive circuitry around this, this crystal at all. And we want our loading capacitors to be nice and close to there. Probably something like, let's actually snap those to the grid. Oh. Let's say really get those nice and close and cozy up there. That's going to help things quite a lot. Let me just check if I've got the model for that crystal there. Oh, yeah, lovely. That's already in there. So cool. That's going to be looking pretty good. We've got our reset circuitry here. I'm actually going to move this all the way over to the other side of the board because with our serial wire debug connector over here, we need a reset pin anyway, so we might as well just get this out of the way. It's not timing sensitive or anything like that. So we can get rid of that. What are these pins doing here? 22. What's R10 doing? It's kind of interesting. R10. Oh, it's on sheet 2 here. Oh, it's, of course, it's for that. It's a low pass filter for that potentiometer. Cool. Well, while we're getting things in place, this decoupling capacitor for our LED can go there. They're more or less in place. What else do we have? I'm just going to select all this and bring it up here. I know one of the toggle switches is just a dummy that I was using to kind of jot out some schematic stuff, but let's start looking at our power here. So in fact, our ADC is probably a better place to start. So where is U4? And I should change that to IC for the designator. And then we've got some supporting components. So 62, 63, 42, and 44. All right. C62, move C63, C42, move C4, move U4 here. So this is our ADC. Now, going to try and segment this into, it's going to be hard with those LEDs, is the only thing, but we can try and segment it into analog and digital sections of the board. So down here is going to be all of our kind of our higher speed digital stuff. These addressable LEDs aren't particularly high speed. So it's okay. We might just run the traces on the other side of the board, perhaps. Or just keep them really nice and separated so we can have a solid ground plane underneath. But then our ADC, we're going to turn around this way because this side is our digital interface and this side is our analog pin. So let's say that it's going to go somewhere there. And then we've got these decoupling capacitors. Need to go around it here. Now going back to our schematic, 2 of them are connected to the analog side. So I think, maybe not. So see 42 and 44 need to be close to 16. Two. Go. So always put the smallest closest. 44. And what's that ground pin there on 14? Is that's analog ground? Okay. So digital ground. Okay, so we want to keep, basically we want these capacitors to be close between 16 and 9, and then these ones between our VREF and our analog ground. So what we're going to do is pin. Oh, why is it all the way over there? Ugh, that's not nice. Let's move those out of the way. They don't need to be there. Ooh. Care about those, do we? Move it down here a bit. Don't care about that either. Okay, so 42. Such a frustrating place for the pins to be. Now we have to sort of do that, and then these need to go between the analog supply. So we're going to make sort of a 10 microfarad and 100 microfarad. Make them as close as we can get those right up to those pins. This is a good example of what I was talking about before, where you've got a quad flat pack and you've got this pair of power pins, and you want to orient your capacitors like that so you can get them nice and close. Really reduce the inductance between those lines, because inductance is going to oppose changes in current, and that's the whole point. So the decoupling capacitors are there. With a digital chip, when you have a sharp edge or a transition, that's going to draw more current. It's going to want that current instantly or as close to, right? And if you have your decoupling capacitors really far away from this chip, then you're going to have a higher inductance, because the PCB traces have this inherent, they've got parasitic capacitance and inductance and resistance to them. They're not perfect ideal traces. And also the thinner it is, the higher your inductance is going to be. So you want them as close to it as possible with big wide traces to really reduce that inductance, because we don't want to oppose changes in current. We want to allow that current to go through freely. That's the whole point. Bring those down a bit here, get that decoupling away from the analog side, because this is sort of the analog side, the sensitive analog circuitry, which we want to steer clear from. What I'm going to do is I'm going to change the order of these channels so that it makes the PCB routing a bit easier. Of course, that's going to go somewhere there, more or less. What else have we got? We've got our PWM to DAC outputs. So that's going to use some ICs, so IC1 through to IC3, and then also Q1 through to Q5. So let's get those. Wrong tab, let's get those. So where's... this is going to go in our analog side. Our digital side. Down there, show... move IC2 and move IC3. Then basically got all of this section is our DAC stuff. So select all of that. Move it over here. Oh, I forgot something. Move it over there. It's quite involved, isn't it? You might be thinking, oh, geez, look at all that circuitry. It surely would have been better just to use a dedicated DAC. But this looks like it's going to be a pain to route, but it's actually just 5 things replicated, so we can copy a lot of the PCB layout. Now, looking at it, this is not going to be overly fun to route. I can see our PWM lines are coming from, if we scroll in, 1, 2, 3, 4 coming from there, and 5 will be somewhere else. So they're probably going to have to come down here to that connector. So I think that we might want to maybe change that a little bit to give ourselves some more room. Either way, they're going to have to go underneath. So you see, thinking about how you're going to actually route your board while you're placing it really saves you some headache in the long run, generally. A couple of options. We could change this, move it up here somewhere, so that and then we route those traces underneath. I'm less inclined to do that. I want to try and keep this to a 2-layer board if possible. So I think that's probably going to... I'm either going to have to move it right out of the way over to here, but then I'm going to have those spire lines running right across, or bump it up to here. So I think I'll have to. Yeah, probably going to have to be somewhere there. I wonder if we actually... That probably gives us more room, actually, leaving it in that kind of configuration. Then we can put... I just don't want it to be too close, but I have to bring it down a little bit to stay away from those analog pins. There. Try and keep the center of this at least just kind of in line with those pins so we can have some sort of delineation between our analog and our digital sides. There. And then nice and close there. Okay, that's looking good. Got a quick save. And yeah, we're going to have to squish all that into there, I'd say. So actually not going to be the most straightforward layout. This is going to be really quite densely populated. We've got our switch. Honestly, completely forgotten about this. Our switch pads and our power. We do need to take a look at our power section of the circuit. Haven't properly finished that. It's going to go somewhere in here. It's not going to be the, end of the world. And looking at this board, we can see roughly where the switches might need to go. So I really hate those connectors. They're so big and bulky. But I'm thinking we can probably just put them on the underside of the board. You know what I didn't consider? I didn't consider these standoffs and the placement for those, because they help secure the bottom board into place. Dang. Okay. All right. Let's think a little here. All right. I'm going to quickly do some measurements on this board. So I'm using the bottom board because it's already got them out of here. Now, it's 30 mils more or less between the holes, between those two, and then 50 mils between the two wider holes. So 30 and 50. So 30 between there. And these are, what size holes are these? These are, so they're going to be for so they're 2.8 mil. So I'm just going to put some M3s in there for now. Let's just go and put some holes in there. Okay. I can't even think. I just want to put drill holes. I'm just having a mental blank as to where. Here we go. Non-plated through hole. So what do we say? Let's go back to metric for a minute. I need to be. It's actually 2.8 mil holes, so we'll make them those. So 50. So you can see there's the longer placement and the shorter placement. So if we're facing that on the design, let's put that at 45 just for now. This is all just for now. Then one at -5. At Let's say 15. That gets us our 30. All right, we can place one over here at 35. Oh, yeah. I may have been a little bit premature in my, yeah, cool, let's place some components because I completely forgot about these. Let's make them aligned at, sure. Let's just call it minus. For now. I'll actually measure more accurately where they need to go vertically. This might not, I don't know what. Oh, what's in around there just left? Do we have room to extend the board a bit? I might actually. We might be able to just bump that board out a little bit. This might not be quite as disastrous as I thought. It pays to show. Double check you've got everything first. Okay. I mean, I don't know why I made that cutout so big as well. That I think I can solve a lot of this squishiness here because we can actually bring this out a reasonable amount. That's 36, and then we can bring that connector back a bit if we want to. Probably going to need to go just a pinch more. Okay, I'm going to save this and push it to a 3D PCB first so I can see how everything's fitting together because I want to get I'm a very visual learner. I need to get a visual sense of how things are fitting together in order to really know if I'm on the right track or not. So, okay. And then there's a file. How's it looking? There should be a reasonable enough amount of room there to. Oh, okay. Extended it too far. That's clear. So we're going to have to take a little bit extra off it. But, you know, in terms of the whole, I don't think that's going to. Yeah, we've got enough room for that. Definitely going to have to bring it back a little bit, but it's okay. We can make a very sort of unique shape PCB. I need to actually work out exactly where these holes need to go first. So how far from, what's a good reference to go off on this PCB? All right, let's measure from the LED on this side. It's probably going to be as good as we'll get. So it's 15.5. And thereabouts. And what are those LEDs again? They're like 6.5 mils, 6.25 mils, I think. 2.25, and it's actually more like 15.5. It's 15.5, 6.25. Let's say 6.3 to make it easy. So 6.3 divided by 2 plus, I've already forgotten what that measurement from the hole is. So let's have a look. It is that really is. Now I'm measuring a bit better. Yeah, it's definitely 15.6. So from okay. Okay, so 3.95. 15.6 minus 3.15 is going to give us from the center of the LED to the outer edge of that hole, and we know that that's 2.8. So let's go minus 1.4, 11.4. a bit. So 11 mils from that LED, and that LED is 28. Okay, it's a bit further than I thought, so they have to be 17. Actually, from that. Wrong dimension. 31.5. That's what, 11. So okay. That's okay. That's okay. 31.5. All right, so it needs to be 42.5. Okay, that's actually super helpful because we can just bring all these holes. Now we've got the relative spacing. Makes this whole conundrum a lot easier. Very nice. Wait, no. No, it makes it much worse. No, this is not good. Whoops, did not want to rotate that. That makes it much worse. Because now that hole needs to be way out here. That's not good. That's not good at all. Actually, it might not be too bad because it doesn't need it just screws there. It could be under there. There's nothing that needs to extend up here, is there? Okay. Okay. Now I need to look at the vertical spacing because that could bring us unstuck here. This is really hard to measure. I'm trying to measure these. If you see those standoff holes against the LEDs as a point of reference. This is probably should have desoldered that switch. Might make it a bit easier. Just wondering if that's a job for next week. I think it is. I think we might call the stream there. We've been going for an hour and a half. That's not a bad effort. So you can see we've already got some of our PCB component layout done. Oh, that 3D model needs to be flipped. But yeah, things are looking good. We just need to solve this little problem with the hole placement. I suspect we might be lucky in that hole probably needs to go up a bit, and it's going to fall somewhere about there under this free space of the on that PCB, which is going to be really quite fortunate for us. So yeah, we'll leave that there. Save everything. I hope you found this useful. A little bit smaller stream than last week, but yeah, leave a comment down below after the fact, and we'll check it out. And love to hear your thoughts and feedback on this project so far. That's all for today, guys. Have a good Tuesday. Bye for now. When I can find the end.